So here's time, and here are some particles. 1, 2, 3. Here, I'll put a fourth one here. These are the kinds of diagrams we think of as contributing to the S matrix. And they correspond to calculating in the interacting vacuum, phi 1, phi 2. It's time ordered, so I can do whatever I want, but just make it a little more time ordered. So, just a quick reminder of why you would think that things would free up asymptotically, so that you would even talk about the S matrix as between free states and free states. Even at tree level, the rough idea is, in fact, it is the idea, and you can check by doing the structure refinement diagrams in perturbation theory, is that the interactions are restricted in space-time by the off-shellness saying. Let me just draw a picture. So for example, if we were doing some scattering, again, this is time like this. In this kind of case, this is an off-shell line. Can't be on-shell. Let's say I'm doing phi cubed field theory or something. This would be an off-shell line. So this separation in space-time can't get too large. At least, let me say n phi is not 0. The little analysis we did about asymptotics of Green's functions would say this can't get too large in any direction. If this is real space-time, you can move this like this. As you're integrating over this, they're somewhere in the same vicinity, roughly given by the Compton wavelength of n. Okay, that's what the asymptotics of the Green's function tells us. So therefore, wherever this, you can think of this as roughly some fuzzy event in space-time. Fuzzy because there's actually two events, but they just can't get too far from each other. That means that way before that, you basically had free particles in perturbation theory. Okay? Way after, you have something like the same thing. Then you say, oh, well, maybe I was doing this case. Okay? 3 to 2 scattering. Well, okay, same thing. In perturbation theory, we see how this S matrix construction works nicely. It says that wherever there are interactions, they're either, the interaction points themselves are pretty local in space-time. But even as you connect things up, you're using off-shell lines, which basically restrict you to some locale in space-time, long before which everything is free, and long after which everything is free. And as long as I work to any finite order in perturbation theory, I don't really see the flaw in that. Okay? At least in tree level, we don't see the flaw. So one thing that can happen, maybe these are all of the exceptions. If you have massless particles and you look at a mass, if this was a massless exchange, something massless, there's a subtlety in the sense that the asymptotics do allow, of the Green's function, the massless Green's function, if you like, the Compton wavelength is 0, is infinity. Is that right? Compton wavelength, yeah. So the Compton wavelength is infinity. So principle, there's not much suppression if these 2 points are very separated in space-time. And we know that there are subtleties, or some of you already know that there are subtleties associated with S matrix in the presence of massless particles like Coulombic interactions and so on. We see this even in non-relativistic scattering. Fine, let's not talk about these massless particles. That's a real case of infrared divergences. And there's suitable amendments of the notion of S matrix which caters to it, so when it's done. Another one, what if you have, I mean, I'm saying it pictorially, how I can go to 10th order in perturbation theory, and it'll always just be some region of space-time based on the asymptotics of these Green's functions. They don't allow you to, off-shell lines are not allowed to get too far away from the off-shell vertices that they connect are not, the vertices connected by off-shell lines cannot be too far away from each other. However, that's a sort of perturbative statement. What if there was some non-perturbative thing where I had to, you know, you could imagine that you just keep drawing G's forever. And so they just keep on making you interact forever. That would undercut the idea that everything that can possibly happen is captured by this notion of an S matrix between 3 states. Indeed, it does undercut it. Indeed, it does break down. The classic example is the hydrogen atom is held together by an infinite in perturbation theory. You would try and describe the hydrogen atom as a result of an infinite number of exchanges of virtual photons. It's not the masslessness of the photon that's doing the work. It's the non-perturbative nature of the hydrogen bound state. And indeed, that screws up thinking of electron-proton S matrix in the way I've been trying to motivate. It undercuts the fact that there are interactions going on arbitrarily early or arbitrarily late in time. But there's a cure. The cure is just include bound states as part of the in-states and out-states that you could have. Okay? Once we add them, stable bound states, to the set of things that could be in the in and out sector, then the S matrix comes back alive again. For example, everybody knows the proton is a bound state, and we have no problem talking about the proton S matrix. Proton-proton scattering S matrix. Okay, that's not what I'm talking about today. I'm just pointing out that these interactions which are non-perturbative, which need to be resummed by some other method, can undercut the S matrix. And we have our own baby version of it, which fortunately is easy to deal with. Here's the baby version. For the camera, I say that, of course, I don't think of any of you as babies. I treat you with respect.
Can I ask you a quick question?
Yes.
So this step where you added a bound state in the Hilbert space along with all the free particles, did you put it by hand to save this matrix, or
Yes.
could you write an equation where it would look like there's a new state? In other words, could you do something like summing those infinite things and you say, okay, this is a new state that I should consider because the math is telling me put that into your set of states, or
Yeah. The real rule in the S matrix is that it's not that free particles come in from infinity. As you're about to see in 1 second, there are no free particles in an interacting theory in any sense, ever. The correct rule is all the stable particles, all stable states should be listed here. Stable states that can live in isolation. Okay? I know that the neutron can be stable in the nucleus, but I should not list officially. I should, for a real S matrix, infinity, I should not put the neutron here. I can put the proton here, because it's absolutely stable. So that's the idea. So the rule graduates from the tree-level version where you say, oh, just put the particles, whatever's in the Lagrangian, just put it in. Instead, the deeper point is, what's this stuff. And the insight is that stable things, you send them in, come from the infinite past, they're stable, they're not going to decay en route. They're going to collide, this, that, and the other, and then out goes some particles. Now, this is where the other line comes from. Yeah, when you scatter these very stable states, you might, in the process, produce some unstable particle, which travels and then decays en route. Again, because it's unstable, after some time, all such particles have decayed away, and you're back to only the stable guys going off to infinity. So again, when you think physically about why you thought there was an S matrix and what you wanted it to be, it's between stable and stable. Stable states in isolation.
So then let me rephrase and ask, would I know that from experiments, or would there be some...
Yeah, you could know it. You could So there are real experiments and Gedanken experiments. In real experiments, you would guess it, okay? Because there's no amount of information that would ever convince you that this particle might not be. The proton could decay.
Sure.
Then there would be a notion of an effective S matrix. That is, it's as if it didn't decay, and it's good enough for LHC purposes because I really don't care about infinite time at the end of the day. It's a kind of idealization. So there are all sorts of approximations of that. But in Gedanken experiment, where in principle you can say, well, give me all the information accessible to a, in principle, experimentalist, then yes, that would include all the stable states. And that would tell them the list of things to plug into that S matrix, bra and Ken. And to the theorist, again,
so
calculate, if you are seeing, it's harder on the theorist. The theorist actually has to know in advance.
Exactly, and so how...
Oh my gosh, no, thorium, this, I think that one is stable. Better include that in my S matrix. So they have the harder problem. Remember, even the hydrogen atom is a very difficult problem if somebody hadn't taught you the trick for solving it. And especially when you're trained in terms of Feynman diagrams, you can try and reproduce the solution to the hydrogen atom, which you can do. But it's not like you would do it like this, because it actually is resumming an infinite set of diagrams, which are infrared singular in the sense of Feynman diagrams, and you resum them in the right way, and then you get the hydrogen bound state. So spotting that some bad behavior is going to kick in perturbation theory, and you resum that, and that'll give you a bound state, which you should include the S matrix in states, is not easy for the theorist. The theorist is flying blind. So often in practice, we get it from experiment. No theorist anticipated, and no theorist can yet prove that the proton should be an asymptotic state. So we got it from experiment.
So there's no algorithmic approach to list down all these states. You
Yeah,
just
that's the problem.
kind of guess it or use something else.
Yeah, in any model, in any field theory worth wasting time on, it's not an easy, there's no algorithm. And indeed, the set of stable structures, which can be stable in isolation, is incredibly large. Right, stable nuclei, stable this, stable that, stable tables, all that. So, and any of these things can come out of the S matrix. Once you decide that something is incredibly unlikely in the S matrix, you can throw it out. So, for example, in field theory, like in the standard model, you might have scattering electrons, and you might say, oh, there are some stable magnetic monopoles that I can list as stable states. I, as a theorist, can see that they're even there. You have to be a clever theorist because they're non-perturbative in some way. And you say, I can see that, so I should list them as possible out states. And then you say, oh gosh, then I have to do a non-perturbative computation to figure out what's the amplitude for that. Is that going to affect what I see in SSE or the LHC or the cosmology or whatever? But the quick thing would be the insight which we have, which is that the amplitude to produce such an exotic state is also non-perturbatively small. And it's so much smaller than anything else you can throw away. So we have various approximations for keeping sane. But the worry is always there. That's what I'm saying. You can never stop thinking. And become the robot algorithmic manipulator. So here we see, in our case, we see a classic case of this. Even when the particle escapes, far from all the other particles, it can interact with itself. Sorry, so let me make this guy, our scalar. It can interact with itself, or it can interact with other particles in the form of self-energy. So let's say this scalar is stable. Remember, that's the case we've just been working on, where the scalar is actually unable to decay into these two particles. But virtually, it can sort of decay into them and come back. And that's the thing we've been studying. And these interactions in space-time go on forever. As long as you have that scalar, it's always able to virtually decay and then come back. And I can never stop from thinking about the interactions. Again, terrible disaster. It's undercut the notion of S matrix, and so we have to fix it. And this is the easiest of the ones to fix. Okay, we've only been doing perturbation theory. This is a problem that appears in perturbation theory. Hence, it has a perturbative solution, and we should do it. So, so when I calculate this, when I calculate Green's functions, I'm getting something that has this structure. So for the moment, we're not doing S matrix, we're just calculating this correlation function. Yeah.
In a free theory, the scalar cannot decay, can it?
Correct.
It cannot. And anyway, we can consider a time-dependent Hamiltonian where
You can.
So then we can make remote
If you
parts.
consider a time-dependent Hamiltonian, you are in good shape. But the world doesn't give us those. So, let me forget the world. I don't care what the world. Lorentz invariance does not give us that.
Okay.
Time translation and symmetry. So the theories we're studying, which are governed by Poincare symmetry, do not have that feature. So instead, we use this intermediate thought, what would life be like if you turned off the Hamiltonian after a finite amount of, the interactions after a finite amount of time. We use that when we talk to each other about how we motivate this object. You'll often hear in a discussion, well, let's imagine we shut off the interaction. But you have to ask, why do we think anybody shuts it off in the real world? Just for our mathematical convenience. We don't. Instead, when you play with the Feynman diagrams that you are considering, at least I think you should start perturbatively. And you start to see, oh, I see the interactions are themselves shutting off after a long enough time. Because of a physical insight, which is that these interactions require these off-shell particles, and these off-shell particles are constrained in how much space-time they traverse. I think it's that kind of locality that is shutting off the interactions. It's not because I formally shut off the interactions in a time-dependent Hamiltonian. But indeed, if you did have a time-dependent Hamiltonian interaction term, none of this problem Okay, so let's imagine that we're calculating this Green's function. It's not an S matrix yet. This is just it. Okay? And when I'm drawing these blobs here, remember this was my notation for the dressed propagator. So dressed by loops, just like the kind that we're doing, but it could be however many loops you want. Now, what happens is I take these points 1, 2, 3, 4, 5, 6, 7 to plus or minus space-time infinity. This thing starts to behave like so starts to behave like some Z on shell. This thing, of course, is the Fourier transform of this thing is, of course, I over p squared minus okay. So, in total generality, this is just the Fourier transform of this. At least we're not dealing with infinities for a second. We're just dealing with everything being finite. But we know that as you take these points far apart, the part of this that you end up probing in the Fourier transform is the part which is the residue, the pole in here. Okay? By Z on shell, just to distinguish it with all these other Z's that came up with infinities, all I mean by the Z on shell is the residue of the pole. Okay?
Why is that not 1 already? By all the choices that we made about A and B and Z.
There, that's one. I made that choice. But can you see why? In fact, you should not be able to. Can you see why when I find the pole, this is only for p squared, this is for p squared near m squared physical. Why should there not be some finite residue? Okay.
It's sort of an expansion, so you will get something.
You'll get something.
Right.
It's exactly the same sense in which this is not the position of the pole in general. Let us say all of this equals 0, and that'll drag this object into the game. Okay. So the best propagator. So I mean this only, I mean that this is approximately this only under the Fourier transform sign. I'm only planning to use these expressions for long time traversals. Then I have the right to just think in terms of this rather than the full function that we see here. Okay. So this thing yeah, the interpretation of this picture is there are these operators phi acting on the vacuum, and they have some efficiency, which we have to determine, I guess next time. They have some efficiency for producing the particle. The particle has to travel a long way, so it's on shell. So there is some efficiency for the operator phi at the point x1 to produce an on-shell particle. And this is that efficiency, obviously. Okay? Phi is 0. Then, once they're produced, there's an S-matrix scattering that's going on. And you end up producing some particles which are on shell. That's all that the rest propagator was trying to tell you, is to say, please go on shell, but to the correct on shell. Okay? And then there is some efficiency to absorb that particle. Okay? Again, we have to figure this out. We have to deduce this. I'll do that next time. And so, what we're saying is that 1 to 7 goes to infinity in the usual sense, that this Green's function is being factorized into the S-matrix element, which we'd love to get our hands on and isolate, times these efficiency factors, which you naively would have said, oh, that's 1 or something, right? But now, because of all the Z stuff, we better be careful, so we'll do that next time. And that's it. So if we want to isolate what the S-matrix element is, all we have to do that's different from what we ever did before is to figure out what the true efficiency factors are. Okay? And that'll involve exactly this factor, as we'll see next time. Okay, so let's stop there. I would have liked to just give you the punchline. But we're out of time. Let's stop. This is exactly where we should take off the next time. What is this efficiency? It's not hard to see. That is, for long-range scattering, it's just this root Z. Reinterpret this. I've actually said this earlier. If you reinterpret what this means, it's the efficiency for phi to send a particle to another phi over long distances so that you're approximately on shell. And that efficiency we usually canonically call it 1. But now I got this extra guy in there, so it's root Z. So other than some root Z factors, business as usual. And we'll do that next time.